Hi everybody, my name is Vlad Dramov, I'm a freelance motion designer, and today we're going to be creating this plane assembling effect. It may seem complex at the first glance, but it's not very hard to do. But anyway, there is a couple of interesting techniques behind it. And as an auxiliary tool, we're going to be using mobs from Intagma. Mobs is some kind of mimicking the behavior of a MoGraph model from Cinema 4D and makes the life of a motion designer in Houdini easier. And the model we're gonna take from free3d.com. It is already UV unwrapped and we will need that in the future. Okay, let's go. First we need to import our geometry. Traditionally it comes huge and we need to scale it a bit. And rotate. Okay, let me tell you about the principle behind this effect. We will take our 3D model and convert it from 3D space to UV space, to 2D space. Then we're gonna cut it, and then we will convert it back to 3D model. Okay, first let's check our UVs. I pressed space 5 for switching to UV view. And now we can see that every single UV island is intersecting with others. We don't need that, we need to make every island to take its own place. We can do that with the help of the UV layout node. Literally, it makes all the job for us. Space 1 to go back. So now we need to convert it from 3D to 2D. We can do that with the help of a single line of the Vex code. We will make it with the help of the Vertex function. It takes vertex number, attribute name, and returns attribute value of current vertex. We need to take UV attribute and just place it to our position. So now we are getting something like this. It's not that much that we need. It's because our geometry is intersecting each other. We can fix that by splitting geometry by UV seams. And we can do that with the help of Vertex split node. Let's give it UV attribute. We can see that our geometry is a bit glitchy here, but we can fix that easily by resetting the Z component of the position. Let's delete our normals so we can easily see our geometry. So now we need to cut our pieces. We will be cutting only big pieces and we will not touch the small ones. We will make it with the help of the for each loop, where we will take every single separate piece and cut it. But before that, to tell Houdini that it needs to take our geometry by pieces, we need to assemble it with the help of assemble node. Assemble node creates name attribute that we can visualize, and now we can see that our geometry is now assembled by the pieces. So now we need to measure the area of each separate piece. We need to tell measure node to accumulate area not by every single polygon, but by the whole piece. To do that, we need to point our freshly created name attribute. Okay, we can see that we have the area now. Each primitive stores it according to the name attribute. Okay, so now we need to get rid of the pieces that we don't like. Delete by expression, and let's say that we need to delete everything which area is below this value. And we're getting the pieces that we may cut now. But small pieces we also need, and let's duplicate the delete node and set delete non-selected. And we're ready to cut our geometry. Let's do for each named primitive and check if it works. Yep, it works. So a couple of words about the splitting algorithm. We will take separate piece, build a box around it, convert its edges to lines, extrude these lines, and then use this geometry as cutting geometry. The box node has single input, which takes the geometry to build the box around. Here's what we get, but we can see that we have intersecting geometry. As you can see, we have a couple of polygons on top of each other. With the help of clean node, we can fix that. We need to consolidate points, fix overlaps, and we don't need to delete overlap pairs. Okay, let's set primitive type to polygon mesh. I think this amount of edges is pretty enough. Okay, let's convert it to lines and extrude them. We need to tell poly extrude to use point normals as the direction for extrusion and point it to existing normals. But now poly extrude is giving warnings because we don't have any normals now, so let's create them. And we're ready to extrude. Let's set some small distance. I can see that we can move it a bit. We need to move it in Z-axis. So we will be cutting the piece by the help of Boolean fracture node. First input takes geometry that needs to be cut, and the second one takes cutting geometry. We can see that we are getting whole now. To fix that, we need to tell this node to treat our geometry as surface but not as solid object. This node not only cuts the geometry but also creates name attribute like the assemble node does. We will need this attribute in the future when we will be packing our geometry. Okay, let's check all pieces, turn off single pass. Yep, it's cool, but as you can see we have some extra points that we need to delete. We can do that easily with the help of clean node. Let's merge all this stuff with our small pieces, and now we need to convert this back to 3D space. We will do that also by just a single VEX code line. First input we'll have our cutted geometry in 2D space, and the second input we will use as the source of the 3D geometry. What we need to do is to get 3D coordinates by UV coordinates. And these 3D coordinates we have in our initial geometry. And as UV coordinates, we have now the position of each point of our cutted geometry. As you can remember, we converted our 3D geometry to 2D space, to UV space. So we can do that by the help of UV sample function. It takes second input, 1 is for second input, 0 is for first one, saying which attribute we need to get from the second input, and pointing the attribute by which we are going to get the position. In our case it's UV. And we need to point the UV coordinate. In our case it's position now. Okay, we are getting something like this. Actually, we didn't aim for this, and we will try to fix that. Okay, I figured out what happened. As you can remember, in our first attribute wrangle, we zeroed out our Z position. We did that for removing our stretching geometry. And because of that, our geometry converts back to the 3D space in a messed up way. So we need to zero out our Z component not on our geometry, but on our UVs. Okay, we will use another attribute wrangle, tell it to run our vertices, and zero out the W or Z component of the UVs. Okay, now it's everything on its place, and our geometry properly converted back to the 3D space. Okay, so what we are going to do now? We need to convert all our pieces to the format that MOPS understands. First, we need to pack them. Let's take sample node and set the checkbox for create pack geometry. And as you can see, we have almost 2000 packed fragments now. And to convert it to the format that mobs understands, we will use mobs convert node. So let's try to transform these pieces somehow. First we need to use Falloff. We're gonna be using plane Falloff. It's an analog of the plane effector from Cinema 4D. Everything this node does, it creates this Falloff attribute and gives it this Falloff value. We can check this in the geometry spreadsheet on the points. As you can see, it's changing now. And next we will need to use mobs transform that will take our mobs Falloff and transform our pieces by this Falloff. Let's try to move it by some value. As you can see, our geometry really moves, and we can control that by controlling the Falloff value in the mobs plane Falloff node. But the problem is that all our pieces are moving simultaneously, all at the same time. Why is this happening? Because all our pieces are oriented in the same way. To do that, we need to reorient them according to their normals, so every single piece could move in its own normal direction. Now you can see by our geometry that we don't have proper normals. So let's create them. We need to do that before our assemble node. And we need to tell assemble node to transfer our normal attribute. To orient the pieces properly, mobs has its own reorient node. Now it gives us an error because it takes orient attribute to orient the pieces in the space. Now we don't have this attribute and we need to create it. To do that, we will use a couple of vex code lines. We will create transform matrix from our normal and up vector and convert it to orient attribute. Matrix is made by the help of makeTransform function. Let's give it our normal and up vector. In this case, up vector is the vector that points in the positive y direction. Second line we will convert it to quaternion and write it to our orient attribute. So now reorient node has everything it needs. We may check how our geometry is oriented in the space by visualizing vectors. We can do that by the help of the mobs visualize frame node. Let's place it after the reorient node. If you don't have the vectors properly displayed the first time, you can switch to another tab of the Houdini and switch back to the scene view. And we can see that every piece has the same orientation as others have. It happened because we didn't set normals to points, but to vertices. We need to fix that. Yeah, now every separate piece is oriented in its own way. Let's check. Yeah, when we turn on the transform modifier, we can see that every separate piece is flying out in its normal direction. You can see that our geometry is a bit glitchy. It's really not the geometry, but our normals. If we switch weighting method to by face area, it will fix that. Okay, we're ready for making animation. Let's take this Falloff value and place the keyframe in our first frame. Let it all assemble in 48 seconds. I'm creating keyframes by pressing Alt and left click. Cool, we are having our first animation. Time to add some variation here. First, let's zero out the scale, so every single piece will scale from 0. The animation looks a bit boring now, because every single piece is flying out as others do. We can add some variation by using some simple vexpression. As you can see, the translate parameter is responsible for moving the pieces in the space. What we can do is take some random value and multiply the translate parameter by this value. Let's take random by the point number and add some seed. But random function returns values between 0 and 1. We can refeed these values to values that we like. Let's take values between 1 and 8. Yeah, now it's getting more interesting. Now we have our separate pieces flying out in their own way. Now it's looking a bit messy because big pieces are flying with small pieces. Let's take our small pieces and move them to some small amount. And big pieces, let's move by bigger amount. To do that, we need to know the area of each separate piece. Actually, we calculated our area before. We have this area attribute, but now it's not transferred to our packed geometry. So let's fix that. But now this area attribute is stored on primitives, and mobs transform modifier is using points. And we need to promote this attribute from primitives to points. Okay, let's modify our expression a bit. Let's multiply our translate by the value that is equal to 0 for the small pieces and to 1 for bigger pieces. Let's create float variable called multArea, and we need to refit our area attribute. But first let's check which values does it take. So it goes from 0 to 0.03 approximately. First parameter is the attribute itself, second one is the minimum value, third one is the maximum value, and the final values will be 0 and 1. And we can multiply all this stuff. And now we can see that small pieces are not much moving now. But now everything assembles simultaneously, and it's not very interesting. We need to add some variation to it. And we're going to do that with the help of the chops. We will be retiming our mobs Falloff attribute, which controls our transformation. So let's create chop network and transfer our mobs Falloff from subs level to chops. We can do that by the help of the geometry node. Let's point it to our null that we created before. Attribute scope will be our mobs Falloff and rename scope will be the same. Okay, let's switch to motion FX view and check our attribute. We can see now that we have just a single line here. It happened because the method is set to static. We need to set it to animated. Our parameter is animated. It changes during time. We can see that we have almost 2000 channels now, which are changing from 0 to 1, but they are changing simultaneously, and we don't like that. We need our signals to change in different moments of time. To do that, we need to use shift node. Shift nodes shift signals in time, and if we're about to change scroll offset parameter, we can see that now we are changing offset of all the signals at the same time. We can randomize that by using some simple expression rand and point it to the C. The C variable stands for current channel number. And now we can see that our signals are changing in different moments of time. So now we need to transfer our mobs Falloff attribute from chops back to subs. Let's create a null object in our chop network and call it toSub. And point it here. Method is animated, as you can remember. Channel scope will be mobs Falloff, and attribute scope will be the same, mobs Falloff. So we are telling which channel we need to take from chops and to which attribute we need to transfer it. Now animation is a little bit spread in time. To increase this spread, we may add some multiplier to our expression. Beautiful! We can make it even softer. To do that, we can use lag node. It does the thing, it softens the signal a bit. So now the pieces are reaching their final position a bit softer. We can even fine-tune our animation by changing our animation curve. I'm shift-clicking the Falloff value to show the animation curve. Let's move these keyframes tangent a bit on the side. So at first they're quicker, and by the end of the animation they're moving slower. We're getting something interesting now. Also, we can play with the seed value in our chops expression to get some different results. I like this one more. So that's all. All the links for the sources I will provide in the description of the video. Thank you for watching. Goodbye.